A very good morning to one all present here. This is Bharat, Assistant Professor, Department of Electrical and Electronics Engineering, SNS College of Technology, Coimbatore. I'm here before you to present the topic. The next topic in our lecture series is the per unit representation. The per unit representation in a power system is a very important thing. So, how do we represent each quantity? We have units for each specific quantity, starting from power, voltage, current, etc. But what is this per unit representation? That is what going to be today's topic, and how we are going to calculate this per unit, and how we are going to continue with the change of base formulas for different finding out the different areas in the per unit representation. Come, let's get into the video. Per unit. So what is this per unit representation? The basic definition for a per unit is the per unit value of any quantity is defined as the ratio of the actual value of any quantity to the base value of the same quantity as a decimal. So the actual formula for per unit is given as per unit is equal to actual value divided by base value. So this is the exact definition for a per unit. So any quantity you need to take, you need to have a base value. And what is the measured value that is called as the actual value? So when you are going to compare the actual value with the base value, that is actual value divided by the base value gives you the value for per unit system. So this is the definition for per unit. So a per unit is a simple representation. It's nothing but an actual value divided by a base value. So what is the use or what are the merits of having a per unit system? Because we already have different types of methodologies, different units for different parameters and all those things. Now, why do you need another system called as per unit system? So that is what the merits of per unit system is listed over here. So what are the merits? So the per unit value is the same for both single phase and three phase systems. The per unit, once expressed on a proper base, will be the same when referred to the another side of the transformer. Thus, the presence of transformer is totally eliminated. The variation of values is in a smaller range that is nearby unity. Hence, the error occurs involved in per unit computations are very less. Usually, the nameplate ratings will be marked in per unit on the base of nameplate ratings. So these are all the different merits. Why do we go for a per unit system? Okay, so the proper base will be there, and you need not each time convert all the parameters into different forms. Okay, so kilovolt to volt, ampere to KA, or KVA to VA, or MVA, and all those things is made simple by per unit system. And the change of base in the transformer from one phase to another phase is also eliminated in the per unit system. So what are the demerits? If any system has a merit, it should also have an equivalent demerit. But what is here? It is a simple demerit, that is, if proper bases are not chosen, if the base value is not chosen properly, then the resulting per unit value may be high. Observed, such as 5.8 per unit, minus 18.9 per unit, etc. This may cause confusion to the user. However, this problem can be avoided by selecting the base MVA nearer the high rating equipment and a convenient base KV in any section of the system. So selecting a proper base is very, very, very important. Okay, so if the base is not selected properly, then your value may not be within the value of 1. So such times you can get a value of 5.8, 18.9 minus, in that and all you will get the answer. So selecting a proper base is important. We have a small trick for selecting the proper base. That is how this problem can be avoided. That is by selecting the proper base MVA, which is near a high rated equipment. Out of the total system, which equipment has the highest rating, so that if you're going to select, then that high rating equipment base will be easy, convenient for MVA. When it is going to KV, you can select the KV of any part of the system. So these are the various merits and demerits of a per unit system. So the demerits also is a method how to improve. So you can use it. Okay. Per unit representation. How do you represent this per unit? If IB is the base current in kiloamperes and VB the base voltage in kilovolts, then MVA is equal to MVAB is equal to voltage divided by current. Okay, V into I. Voltage, base voltage into base current. Then the base values of the current and impedance are given by base current KA, this IB is equal to MVAB divided by KVB. So, okay, MVAB is the power divided by KVB is the voltage, which gives you the base current. How to calculate the base impedance? So, base impedance is given by the formula ZB is equal to VB divided by IB, which is equal to VB2 divided by MVAB. Okay, so KVB the whole square divided by MVAB. So the base impedance is the formula is very important. So base impedance is given by the formula KVB the whole square divided by MVAB. So VB by IB. So in the previous step, we have calculated the values of base current. The base current is equal to MVAB divided by KVB. We are just substituting it over there on the top. So base impedance ZB is equal to VB divided by IB. That is KVB the whole square divided by MVAB. Hence, the per unit impedance is given by Z per unit is equal to Z ohms divided by ZP. That is equal to Z ohms, that is MVAB divided by KVB the whole square. So this is the formula for Z per unit. So this formula is very important where we use these same formulas for finding out the problems or solution of the problems in different cases. Okay. In a three-phase system, KVB is the line-to-line value. At MVAB is a three-phase MVA. The single-phase MVA is equal to 1 by D into three-phase MVA. So with this, we are going to see a new formula as called as a change of base formula. How we are going to change the complete given network or a grid into a per unit value. That is, you are going to find out the Z per unit mu for the given system. So that is called as the change of base. So Z per unit mu is equal to, so this we can derive with a small derivation that we'll explain in the class. So Z per unit mu is equal to Z per unit given into MVAB mu divided by MVAB given into KVB given divided by KVB nu the whole square. So this is the change of base formula. Once again, I will repeat. Z per unit nu is equal to Z per unit given into MVAB nu divided by MVAB given into KVB given by KVB nu the whole square. So this is a very important change of base formula. So with this formula, we are going to solve some problems as the case example. So one problem what I have taken today is two generators rated at 10 MVA, 13.2 kV and 15 MVA, 13.2 kV are connected in parallel to a bus bar. Okay, so both are connected in parallel to a bus bar. They feed supply to two motors. Okay, they feed supply to two motors of input 8 MVA and 12 MVA respectively. The operating voltages of motor is 12.5 kV. Assuming the base quantities as 15 and 50 MVA, 13.8 kV, draw the per unit reactance diagram. The percentage reactance for generator is 15% and that of the motor is 20%. So here you can use, this is the given data. So you can write down the given data and we are going to use the change of base formula. Z per unit mu is equal to Z per unit given into MVAB nu divided by MVAB given into KVB given by KVB nu the whole square. So with this, we are going to substitute. Okay, we will substitute the different values for the given question. So 10 MVA, 15 MVA, two generators, 3.2 kV and 15%. Two motors, M1 and M2, 8 MVA and 12 MVA, 12.5 kV and 20% reactance. They are substituting different values with the selection of base of 50 MVA. Okay, so substituting all the different values, we get the reactance values of generator 1, generator 2, generator 3, and generator mode 4 as 0.6862, 0.4574, 1.0256, 0.6837. Just substituting all the values, and EG1 and EG2 are 0.9565 and 0.9058. So just substituting all the values, this gives the reactance diagram. So the final thing is called as the reactance diagram, the given structural one line diagram. So with this, we have calculated for the given problem. Like this, we'll take one more case. Okay, draw the per unit reactance diagram for the system shown in the figure given below. Choose a base of 11 kV. So all the data are given in the diagram itself, in the single line diagram itself. We are going to choose a base of 11 kV, 100 MVA in the generator of the given circuit. So what is there in the given circuit? You have a generator, you have two transformers, you have a transmission line, and again this side you have two transformers, you have transmission line and connected to a motor. So this is the complete structure. You have all the data over here. So how you are going to draw the impedance diagram and reactance diagram? How we have solved the same formula in the previous case? Yes. Z per unit nu is equal to Z per unit given into MVAB nu by MVAB given into KVB given by KVB nu the whole square. You're going to substitute all these values and you're going to draw the reactance. So the solution of this, I'll explain in the next video. You just try it out. Okay. So with this, we'll just conclude what we have seen in today's class. What is per unit? What is the use of a per unit system? What is the actual definition for a per unit system? What are its formulas, merits and demerits? We have solved two case problems with an example. Thank you. Meet you in the next class. Thank you.